is about hypothesis testing with one sample. So throughout Chapter 9, we're going to learn about how to set up your null and alternative hypotheses, how to interpret the outcomes and potential errors, distribution needs, and then in 9.5, we will actually get to running the full hypothesis test. One job of the statistician is to make statistical inferences about populations based on samples taken from the population. Excuse me. Confidence intervals are one way to estimate a population parameter. Another way is to make a statistical inference by making a decision about a parameter. So for instance, a car dealer advertises that its new small truck gets 35 miles per gallon on average. So that's the claim that they are making. A tutoring service claims that its method of tutoring helps 90% of its students get an A or a B. A company says that women managers in their company earn an average of $60,000 per year, rather than saying a car dealer advertises that a new small truck gets between 30 and 40 miles per gallon. They are making a claim about a specific value. A statistician will make a decision about these claims. This process is called hypothesis testing. A hypothesis test involves collecting data from a sample and evaluating the data. Then the statistician makes a decision as to whether or not there's sufficient evidence based upon the analysis of the data to reject the null hypothesis. That is what your hypothesis test is. Either you reject the null or you fail to reject the null. The claim may or may not be the null, but your hypothesis test is always about rejecting the null or failing to reject the null. All right, so you need to set up two contradictory hypotheses. So either your mean equals this or it doesn't equal this. Either your mean is greater than this or it's less than or equal to it. Something like that, but they have to be contradictory. Collect sample data. So in your homework problems, the summary or the actual data will be given to you. Determine the correct distribution for a hypothesis test. So that could be a z-test, a t-test, or a 1 proportion z-test. Analyze sample data by performing the calculations, which I will show you how to do in the graphing calculator, and then make a decision and write a meaningful conclusion. So starting with that first step, you have to write two contradictory hypotheses. These are called the null hypothesis and the alternative hypothesis. They have to contain opposing viewpoints. They have to be contradictory to each other. The null hypothesis is a statement about the population that is either believed to be true or used to put forth an argument unless it can be shown to be incorrect beyond reasonable doubt. The alternative hypothesis is a claim about a population that's contradictory to the null, and it's what we conclude when we can reject the null. Since the null and alternative hypotheses are contradictory, you must examine the evidence to determine if there's enough evidence to reject the null hypothesis or not. Again, your hypothesis test is always about rejecting the null or failing to reject the null. After you have determined which hypothesis the sample supports, you make a decision. There are two options for the decision. Either reject the null hypothesis if the sample information favors the alternative, or you fail to reject the null, saying that it could still be true. We're not saying it is true, we're saying it could be true. We don't have enough evidence to say it's not. Super important that you to note, the null hypothesis always has an equal to, whether it's equals, greater than, or equal to, less than, or equal to. The alternative hypothesis will never have equals. It'll always be not equal, greater than, or less than. So that is this note here. Okay, so example 9.1. If we have a null hypothesis saying that no more than 30% of the registered voters in the Santa Clara County voted in the primary election, then we're saying that P, the percent, is less than or equal to 30. The alternative of that would be, contradictory to that, would be more than 30% of the registered voters in Santa Clara County voted in the primary election, so P is greater than 30. We want to test whether the mean height of 8th graders is 66 inches. State the null and alternative hypotheses. So we want to test if the mean is 66. Since that is what we are testing and it has an equals, that is our null hypothesis. The null hypothesis is that the mean equals 66. The alternative has to be contradictory to that. So the contradictory statement to that would be that the mean is not 66. All right, we want to test if college students take less than 5 years to graduate from college on average. So you want to see if the mean is less than 5 years. Since it does not have an equal to, that's our alternative hypothesis. Contradictory to that would be the opposite. So the mean is greater than or equal to 5 years. The textbook likes to just put equals 5 here for the null. That's still contradictory to the alternative. All right, so in an issue of U.S. News and World Report, an article on school standards stated that about half of all students in France, Germany, and Israel take advanced placement exams and a third pass. The same article stated that 6.6% of U.S. students take advanced placement exams and 4.4% pass. Test if the percentage of U.S. students who take the advanced placement exams is more than 6.6%. So we want to know if the proportion is greater than 0.066. Since it does not have an or equal to, that's our alternative hypothesis. Our null is contradictory to that the percent is less than or equal to 0.066. So on a state driver's test, about 40% pass the test on the first try. We want to test if more than 40% pass on the first try. So we are testing if the percent is greater than 40. Since that does not have an equal to, that has to be our alternative hypothesis. Contradictory to that would be that the percent is less than or equal to 0.40. Again, your textbook will put equals here. That's still contradictory to greater than. So that's how you set up your null and alternative hypotheses. Your claim does not always have to be the null, just like it doesn't always have to be the alternative. All right, so next we're going to talk about the outcomes you get with hypothesis testing and then their type 1 and type 2 errors. When you perform a hypothesis test, there are 4 possible outcomes. So you could fail to reject the null, meaning it could be true. And the null is actually true. Yay, you did the right thing. You had the correct outcome. You could fail to reject the null, saying it could be true, when the null is actually false. That's called a type 2 error. You could reject the null, but it's actually true. So you said it's false, but it's actually true. That's a type 1 error. If you reject the null and it actually is false, so you said it's false, and it is false, that's the correct outcome. Alpha, the Greek letter alpha, is used to say the probability of a type 1 error. Beta is the probability of a type 2 error. Alpha and beta should be as small as possible because they're probabilities of errors. They will never be 0. That's just a fact of life, or I guess rarely 0. The power of the test is found by taking 1 minus beta. You want a high power test because that means it's a very, very low possibility of a type 2 error. You are going to see alpha a lot because we're going to use that as our significance level for tests. All right, suppose the null hypothesis is Frank's rock climbing equipment is safe. So then a type 1 error would be a type 1 error is when you reject the null, but it actually is true. So we said his rock climbing equipment was not safe, but it actually was safe. A type 2 error is that we fail to reject the null, but it actually is false. So we say, we think his rock climbing equipment is safe, but in fact it's not safe. Notice that in this case, the error with the greater consequence is a type 2 error. The fact that he thinks his rock climbing equipment is safe and it's not really. Whereas if it really was safe, but he thought it wasn't, he just didn't use it, it's a waste of equipment, but it's not necessarily dangerous. Alpha would be the probability that his rock climbing equipment may not be safe when in fact it really is, so the probability of a type 1 error. Beta is the probability of a type 2 error, meaning that he thinks it's safe, but in fact it's not. So suppose the null hypothesis is the blood cultures contain no traces of pathogen X. State the type 1 and type 2 errors. A type 1 error. Okay, so let's talk about the null first. If the null is true, that means that there really is no pathogen X in the blood. If the null is false, then there is pathogen X in the blood. So a type 1 error is when we reject the null, but it actually is true. So we say that there is no pathogen. I'm sorry. A type 1 error is when, I was right. Sorry. My notes are on my desk a little further away from you. I'm trying to read my own handwriting. A type 1 error is when we reject the null. So we say that there is pathogen X in the blood, or we think there is, but really there's not. Type 2 error is when we do not reject the null, meaning we think it's true, so the researcher believes there's no pathogen X, but really there is. Okay, determine both the type 1 and type 2 errors for the following scenario. Assume a null hypothesis states that the percentage of adults with jobs is at least 88%. Identify the type 1 and type 2 errors from these 4 statements. So the null hypothesis states that the percentage of adults with jobs is at least 88%. So the null hypothesis is that the percentage is greater than or equal to 0.88. So then A, we do not reject the null, saying we think it's true, when the percentage is actually less. So we're saying we think this is true, but really P is less than 0.88. That is a type 2 error. When we do not reject the null, but really we should have, that's a type 2 error. B, not to reject the null hypothesis of when the percentage is actually at least 88%. So we say, we think this is true, and it actually is true. B is a correct outcome. C, reject the null hypothesis when the percentage is actually less, at least 88%. So we're saying this is absolutely false, but really it's true. That is a type 1 error. And then D, reject the null hypothesis when the percentage is actually less than 88%. We're saying this is absolutely false, and it actually is false. That's the correct outcome. So that's how you find a type 1 and type 2 error. All right, 9.3 is about the distribution needs for hypothesis testing. So earlier in this course, we discussed sampling distributions. Particular distributions are associated with a hypothesis test. You perform tests of population mean using a normal distribution or a student's t distribution. Remember, the student's t distribution is used when the population standard deviation is unknown. we perform tests of population proportion using a normal distribution. Usually your sample size is large. The population parameter is mu. So that's your population mean. We use the mean of the sample as a point estimate. Same with proportions. We use a sample proportion as an estimate for the true population proportion. Some assumptions that we make when you're using a hypothesis test for a single mean using the student's t-distribution, which we call a t-test. You have to have a simple random sample from a population that's approximately normal. However, if you're using a t-test, it's okay if it's not approximately normal as long as your sample size is sufficiently large. And you would use the sample standard deviation as an estimate for the population standard deviation. That is for a t-test. When you perform a hypothesis test using a normal distribution, which is a z-test, that's when you know the population standard deviation, which in reality is really hard to actually know. And then you perform a hypothesis test of a single population proportion. So you're saying yes or no. That's a binomial distribution. Either they meet the qualification or they don't. There has to be more than 5 successes and 5 failures in your sample. And then remember that we use a standard deviation of that sample as p times q divided by n, and then take the square root of that. All right, so 9.4 is information with the sample, rare events, and then how do we take the data and make a conclusion? What does that conclusion mean? Rare events, suppose you make an assumption about the property of a population, then you gather sample randomly. If the sample has properties that would be very unlikely to occur, if the assumption is true, then you would conclude that your assumption is probably incorrect. Remember that you are just making an assumption. Using the sample to test the null. When we use the sample data to calculate the actual probability of getting a test result, that's called the p-value. The p-value is the probability that if the null hypothesis is true, the results from another randomly selected sample will be as extreme or more extreme as the results obtained from the given sample. A large p-value indicates that we should not reject the null hypothesis. The smaller the p-value, the more unlikely the outcome, and the stronger the evidence to reject the null. Your textbook has a saying, P is high, the null must fly, meaning if your p-value is high, don't reject the null. If p is low, the null must go, meaning if you have a low p-value, you should reject the null. A normal distribution has a standard deviation of 1. We want to verify a claim that the mean is greater than 12. A sample of 36 is taken with a sample mean of 12.5. So the claim is the mean is greater than 12. Since that does not have an equal to, that's our alternative. The null is contradictory to that, so the mean would be less than or equal to 12 for the null. Draw a graph that shows the p-value of this. You have your distribution. You have 12 in the middle, because that's from our hypothesis. And then the sample mean was 12.5. This p-value is representing the area to the right, because mean is greater than 12. So to the right would be greater of 12.5, which is from the sample. But I still look at the alternative to see where to shade. Our p-value is that area there. This is a low p-value, so if we started talking about claims, p is low, the null must go, we would reject the null and verify the claim. We would say, yes, we support the claim that the mean is greater than 12. A systematic way to make a decision of whether or not to reject the null hypothesis is to compare P to a preset alpha, which is called your significance level. Remember that alpha is the probability of getting a type 1 error. It may or may not be given to you at the beginning of the problem. If it's not given to you, you're going to assume it's 0.05. Okay, so if alpha is greater than P, you reject the null. If alpha is less than or equal to P, you do not reject the null. And then when you do not reject the null, it doesn't mean that you believe it's true. It simply means that you don't have enough evidence to support that beyond a reasonable doubt it's absolutely false. After you make your decision, you write a thoughtful conclusion about the hypothesis in the terms of the problem. So when using a p-value to evaluate a hypothesis test, if the p-value is low, the null must go. If the p-value is high, the null must fly. Remember that if p is less than alpha is what that means. P is low, the null must go. You reject the null, saying that we believe the alternative is true. If the P is high, the null must fly. So if P is greater than alpha, you fail to reject the null. Meaning, it could be true. We're not saying it is true. We're saying it could be true. So, you reject the null hypothesis when P is less than alpha. If you reject the null hypothesis, then the data supports the alternative. You do not reject the null when P is greater than or equal to alpha, which means that the data do not support the alternative. It's a Boy genetics labs claim their procedures improve the chances of a boy being born. The results for the test of single population proportion are as follows. So they are claiming that their procedure makes that proportion greater than 50%. So contradictory to that would be that your probability is still 0.5. You conduct your test. You have an alpha preset of 0.1 and a p-value from your test of 0.025. P is greater than alpha. P is high, the null must fly, so you do not reject the null. Meaning that the data does not support the alternative hypothesis. So there is not enough evidence to support their claim that their procedures improve the chances of a boy being born. All right. Find the p-value for the test statistic for the following null and alternative hypotheses. Okay, so this tells me the fact that it's a z test statistic, that we are talking about a z test with a normal curve. So if I were to draw a picture for this first one, we have a test statistic of z equals negative 1.47, and the null and alternative hypothesis is that the mean equals 5 and that the mean is less than 5. So If I have my normal curve and a z-score of negative 1.47, negative means it's below the mean, so the middle of that normal curve, by 1.47 standard deviations, which is somewhere over here. Our alternative is that the mean is less than 5, so this is a left tail test. So basically, we are looking for this area to get the p-value. It's a normal curve, so on our calculator, we're going to go to that second distribution and use normal CDF. With this z-score, we're using the standard normal curve. So remember that that means it's a mean of 0 and a standard deviation of 1. Our lower bound is ridiculously small, negative infinity. So our lower, when it's at ridiculously small, is negative 1 E99. And our upper, where we want the shading to end, right here is our z-score of negative 1.47. Okay, I'll show you how to do this on the graphing calculator here in a second. I'm just going to go ahead and talk about B so I can do both of those on the graphing calculator at once. So find the p-value for the test statistic z equals negative 1.47 for the following null and alternative hypotheses. The mean is 5, or the mean is not equal to 5. When you have a not equal, that's a two-tailed test, so that normal curve, you're looking at both sides. And so we have negative 1.47 and 1.47 for this area. Remember that these areas are equal to each other because it's symmetric. So if I find this area, which actually I'll do that on the previous problem, I can just multiply it by 2 because I have two areas that are the same side. All right, so now how to do this on the graphing calculator. Second distribution, and I go to normal CDF. Our lower was negative 1 E99. Our upper was negative 1.47, that z-score. It was the standard normal curve, so the mean was 0 and standard deviation is 1. So I get a p-value for that first one of 0.0708 if I round it to 4 decimal places using that normal CDF. So we got 0.0708. Remember that the two-tailed test is symmetric, so it's just multiplying that value by 2 to get 0.1416. All right, so now actually conducting a full hypothesis test. In a hypothesis test problem, you'll see words such as the level of significance is 1%. 1% then is alpha, so alpha would be 0.01. The statistician setting up the hypothesis test has to pick alpha before collecting the sample data. If you are not given a level of significance, the common standard is to use a preset alpha of 5% or 0.05. When you calculate p-values, draw the picture. The p-value is the area in the left tail, the right tail, or split evenly between the two tails. For this reason, we'll call a hypothesis test a left tail, a right tail, or a two-tailed test. The alternative hypothesis tells you if your test is a left, right, or two-tailed test. It is key to conducting the appropriate test. Your alternative hypothesis should never contain an equal sign. And then we talked about the p-value in the last section. P is low, the null must go. P is high, the null must fly. Okay, so if our null is mean is equal to 5 and our alternative is that the mean is less than 5, that is a left tail test because the alternative is that the mean was less than 5. If our null is that p is less than or equal to 0.2 and our alternative is that p is greater than 0.2, that's a right-tailed test because you're going bigger. And then if you have p is 50 and the alternative is that p is not 50, anytime your alternative is not equal to, that's a two-tailed test. And so your p-value is split between the two tails. All right. Jeffrey as an 8-year-old established a mean time of 16.43 seconds for swimming the 25-yard freestyle with a standard deviation of 0.8 seconds. His dad, Frank, thought that Jeffrey could swim the 25-yard freestyle faster using goggles. Frank bought Jeffrey a new pair of expensive goggles and timed Jeffrey for 15 25-yard freestyle swims. For the 15 swims, Jeffrey's mean time was 16 seconds. Frank thought that the goggles helped Jeffrey to swim faster than the 16.43 seconds. Conduct a hypothesis test using a preset alpha of 0.05. Assume that the swim times for the 25-yard freestyle are normal. Okay, so our population in this case has a mean time of 16.43 seconds and a standard deviation of 0.8. So we are told the population standard deviation is 0.8. Because we are told that we have the population standard deviation, this is a z-test because sigma is known. All right, so Frank, the dad, his claim is that with the goggles, the mean time is less than 16.43 seconds because he wants him to be faster than that, right? That claim does not have an equal sign. So that means that that's our alternative hypothesis. The null has to be contradictory to that. So our null hypothesis is that the mean would be greater than or equal to the 16.43. Some other information given to us. The sample size was 15 with a sample mean of 16 seconds. So that's with the goggles. He did 15 25-yard swims with a mean time of 16 seconds. That's all the information we need in order to do this in our graphing calculator. So if I grab my graphing calculator, I'm going to go to Stat. I'm going to go over to Tests. And we are running a z-test because we know the population standard deviation. Input, we do not have the data. We do not have the times of the 15 swims. We have the stats of the 15 swims. So I'm going to go over to Stats and hit Enter. Mu sub 0. This is the number from our null and alternative hypothesis. So that is going to be 16.43. Sigma is the population standard deviation. That was given to us as 0.8. X bar is the sample mean. He had a sample mean of 16 seconds with the 15 swims. So that's what N is. This row is your alternative hypothesis. Our alternative hypothesis is that the mean is less than or equal to, and remember mu sub 0 was this number up here. So our alternative hypothesis is that the mean is less than or equal to 16.43. So I'm going to then go down to calculate. And this gives me my Z critical value or a Z test statistic. So on Edfinity, when it asks for a test statistic, that's going to be Z equals negative 2.0817 for this problem. Or if it's a t-test, it'll be t equals. I find it's easier to make your conclusion with looking at the p-value. So our p-value for this particular test is 0.0187. So I ran my test. I got a p-value of 0.0187. And it says that alpha is 0.05. P is less than alpha. When the P is low, the null must go. So we reject the null. Remember that the null was that the mean is greater than or equal to 16.43. If we are rejecting the null, that means we have sufficient evidence to support the alternative, which was our claim. So at the 5% significance level, and where did I get that 5% from? That's because we're using an alpha of 0.05. We conclude that Jeffrey swims faster using the new goggles. College football coach records the mean weight that his players can bench press as 275 pounds with a standard deviation of 55 pounds. 3 of his players thought that the mean weight was more than that amount. They asked 30 of their teammates their estimated maximum lift on the bench press exercise. The data ranged from 205 pounds to 385 pounds. The actual weights were 3 players said 205 pounds. 3 players said 215. 1 player said 225, so on and so forth. Conduct a hypothesis test using a 2.5% level of significance to determine if the bench press mean is more than 275 pounds. Okay. The claim, the 3 players think that the mean was more than the college football coach saying 275 pounds. The standard deviation of the population is given to us, so that's sigma. That's 55. Okay, so let's go back actually to that claim, though. The claim is that the mean is greater than 275. That does not have an equals to. So that's our alternative hypothesis. The null hypothesis has to be contradictory to that. So contradictory to that would be that the mean is less than or equal to 275. We know the population standard deviation is 55. So this is a z-test, same as before. I'm going to go ahead and go to my graphing calculator and show you how to type this in. So stat, this time we have to put our data into these lists. So we're going to put the weights into L1. So we had players say 205 pounds, 215, 225, 241, 252, 265, 275, 313, 316, 338, 341, 345, 368, and 385. And then we're going to put our frequencies for each of those in L2. So 3 players said 205. 3 players said 215. 1 player said 225. 2, 2, 2, 2, 2, 5, 2, 1, 2, 2, and then 1. So I have my data in my list, my weights, and then the frequency. So now I can go back to stat, over to tests. And again, it's a z-test because we know the population standard deviation. This time, we have the individual data points. Remember that this first spot here, mu sub 0, that is the number from our hypotheses, so that's going to be 275. Sigma was given to us as 55 pounds. Our list, our weights were in L1. Our frequency list was in L2, so I'm going to hit second. L2 is blue above the 2. And the alternative hypothesis was that the mean was greater than 275. So I need to change this to a left or a right tail test. So I get a test statistic of 1.11204 and a p-value of 0.1331. Alpha was given to us at a 2.5% significance level, so 0.025. P is greater than alpha. Because P is high, the null must fly, so do not reject the null, meaning we don't have sufficient evidence to support the claim of the alternative hypothesis. So at the 2.5% significance level, there is not sufficient evidence to conclude the true mean is more than 275 pounds. Statistics students believe that the mean score on the first statistics test is 65. A statistics professor thinks the mean score is higher than 65. He samples 10 statistics students and obtains the scores 65, 65, 70, 67, 66, 63, 63, 68, 72, and 71. He performs a hypothesis test using a 5% level of significance. The data are assumed to be from a normal distribution. This is a t-test because we don't know sigma. We're never given a population standard deviation. Okay, so the claim is that the statistics professor thinks the mean score is higher than 65. So he thinks the mean is greater than 65. Since this does not have an equal to, that's our alternative hypothesis. The null can either be, it has to be contradictory. So, the students believe that the mean score is 65, so equals 65 would be contradictory. You also could use that the mean is less than or equal to 65. Either of those would be fine for a null hypothesis. It just has to be contradictory to the alternative. All right, so we've established that this is a t-test because we do not know the standard or the population standard deviation, and we have our hypotheses written. So I'm going to go ahead and go to my graphing calculator. And we were given all of the individual test scores. Because of that, we have to go to Stat and into Edit. And I'm going to go ahead and erase these lists. Remember, if you highlight L1 and L2 and hit Clear and then Enter, it'll quickly erase all the data. And now I'm going to just type the data into L1. So I'm going to put all of the test scores. And we are not given a frequency list. We're given them all listed out. So I'm not going to have anything in L2. Forgot a 63 there. There we go. Now I have my 10. All right. Next, I'm going to go to Stat. We're going over to Test. And this is a t-test instead of a z-test. And our input is the individual data, so we want data. Now remember, mu sub 0, that is the number from our hypotheses. So our hypotheses both had the 65 in there. Our list is L1. Our frequency is just 1. We didn't have a frequency list. And our alternative hypothesis was that the mean was greater than 65. Remember, mu sub 0 is this number here. So our alternative hypothesis, the mean is greater than 65. So I go down to calculate. My test statistic is t equals 1.978, blah, blah, blah. My p-value, which I find is easier to make a conclusion with, 0.0396. Flip back to the notes. So from our t-test, we got a p-value, 0.0396. It says using a 5% level of significance, so alpha is 0.05. So p is less than alpha. If p is less than alpha, we reject the null. So at the 5% significance level, if we reject the null, that means we are saying the alternative has support, and the alternative was our claim. We can say the sample data shows sufficient evidence that the mean test score is more than 65. Because remember, our null was that it was equal to 65 or less than or equal to 65, and we're saying that absolutely has to be false. So thus that means we have sufficient evidence that the mean score is more than 65. June believes that 50% of first-time brides in the U.S. are younger than their grooms. She performs a hypothesis test to determine if the percentage is the same or different from 50%. So she's not saying that more than 50% or less than 50%. She's just saying not 50%. Okay? So June believes that 50% of first-time brides are younger than the grooms. So her claim is that the percent is 50%. So that is her claim is the null hypothesis. The last two, the claim has been the alternative. But since it has an equals, it's our null. Remember, alternative never has equals, null always does. The alternative has to be contradictory to that. Contradictory to equals would be not equal. She doesn't care if it's above or below. She just wants to know, is it equal or not equal to 50%? Because we are talking about percentages or a proportion, This is a 1 proportion z-test. You don't have to worry about a 1 proportion t-test. Any proportion is a z-test. Okay, you just have to know, is it a 1 proportion or 2 proportion? This is a program on your calculator. Now, some information you need to know. You'll need to know p sub 0, which is the number that's in your hypotheses, so that'll be 0.50. You need to know x, which is the number of successes in your sample. So in the sample, there's 100 first-time brides. 53 replied, yes, they are younger than their grooms. You need to know your sample size. But then after that, you can go to the graphing calculator. And go to Stat, over to Tests. And we want a 1 proportion z-test, so number 5 there. So p sub 0 is the same as mu sub 0. That is, what's the number that's in your hypothesis, or hypotheses. X is the number of successes from your sample. N is your sample size. And this is your alternative hypothesis. Our alternative hypothesis is that the proportion is not equal to 0.5. Go down to calculate, and I get a test statistic of 0.6 and a p-value of 0.5485. So my p is 0.5485. It says we're using a 1% level of significance, so that means alpha is 0.01 for 1%. So p is greater than alpha. If the p is high, then null must fly, meaning do not reject the null. So in this example, though, the claim was the null hypothesis. So really, we're saying that her claim could be true. But if we are failing to reject the null, that means we don't have sufficient evidence for the alternative hypothesis. So at the 1% significance level, the sample data do not show enough evidence or sufficient evidence that the percent of first-time brides who are younger than their groom is different from 50%. And we say different because remember our alternative hypothesis was just that p was not equal to 0.50. Suppose a consumer group suspects that the proportion of households that have 3 cell phones is 30%. A cell phone company has reason to believe that the proportion is not 30%. Before they start a big advertising campaign, they conduct a hypothesis test. Their marketing people survey 150 households with the results that 43 of the households have 3 cell phones. Find the value that helps determine the p-value is p prime. Calculate p prime. P prime is just what's the percentage or our proportion in our sample. So p prime would be 43 out of the 150 households had more than 3 cell phones. And so that's our p prime. We don't even, we can leave it as a proportion instead of converting to a decimal. What is a success for this problem? A success would be, yes, a house has 3 cell phones. What is the level of significance? Anytime it's not given to you, we assume that alpha, sorry, I don't know why that happened. Anytime it's not given, we assume alpha is 5% or 0.05. Draw a graph. I'm not going to, draw a graph here. I'm going to just calculate the p-value by using my graphing calculator. So to do this, I need to start with my hypotheses. The claim would be that a cell phone company has reason to believe that the proportion is not 30%. So the claim is that the proportion is not 30%. Since that does not have an equal to, that's our alternative hypothesis. The null would be that the proportion is equal to 30%. Since we're talking about percentages and proportions, this is a one proportion z-test. It's a program on your calculator. So if you hit stat and go over to tests, there it is. You need to have p sub 0, which is the number from your hypotheses, so 0.30. You need to have x, which is the number of successes from your sample, so that'd be 43. My pen is not wanting to work today. And n is the sample size, so that would be 150 households. And then you would have to put the proportion is not equal to 0.30 because that's our alternative hypothesis. So if you run that test on your calculator, you would get a p-value of 0.7216. So because p is greater than alpha, we do not reject the null. Meaning that at the 5% significance level, we do not have sufficient evidence that the proportion is not 30%. So that is it for chapter 9. As always, if you have any questions, feel free to reach out.